What do you think is the hottest thing in your house? Unless your hobby is forging steel, and actually even if it is, the answer is probably one of these. A light bulb. Specifically, an incandescent light bulb, assuming you still haven't gotten around to replacing yours with LEDs yet. These old ones work by passing current through a thin wire called a filament, which causes it to heat up.
The filament gets really hot. A standard filament operates at well over 2000 degrees Celsius. The idea here is that when the filament reaches this temperature, it begins to emit visible light as well as heat. Therefore, a light bulb converts electrical energy into heat, then light energy, in that order.
So, as you might expect, a standard incandescent light bulb is less than 5% efficient. That means less than 5% of the electrical energy that powers it is given back as visible light. The rest is transferred to the surroundings as heat. So there is nothing useful that energy can really do.
Or is there?
The problem of wasting heat energy is not unique to light bulbs. Nearly 2/3 of the energy used in conventional electricity generation is wasted in the form of heat discharged to the atmosphere. So is there any way we can stop it all from being wasted?
Well, one idea to use this extra heat energy is, heating. This is known as CHP, or combined heat and power, and it's already in use in thousands of power stations across the world. Instead of generating electrical power in a power station, and then using that to heat up water in the boiler, you can simply use the wasted heat energy from power generation to do that instead.
CHP can easily have an efficiency of over 80%, which makes it a good way to reduce environmental impact of energy generation, while also putting the excess energy to good use. But what if we wanted to use that heat energy for something other than heating? Heat energy is great, but it won't power the device you're watching this video on. Now, how can we turn this excess thermal energy into useful electrical energy?
The problem we have with using wasted heat energy comes down to entropy. Entropy is not an easy concept to understand, just ask this guy. But you can think of it as a measure of how disordered a certain system is. To help put this into context, let's go back to that light bulb example. On a molecular level, thermal energy is basically just the kinetic energy of particles. So, when a light bulb gives off heat, it heats up the air around it and causes those air molecules to have more kinetic energy.
Before switching the light on, the energy is just sitting around. But now, it's spread out in terms of the kinetic energy of all these particles. There are now many more possible states this system can be in. A common but sometimes unhelpful analogy is comparing a tidy room to an untidy one. Now, when we talk about disorder, we're not saying that the messy room has a greater entropy simply because it's less tidy and ordered. Instead, there are many more ways for a room to be untidy than for it to be tidy. The messy room has a greater entropy because it can take many more possible states.
With the light bulb, there are more possible microstates for the system, with those fast-moving particles, each of which has a certain speed and position which we have to keep track of. So we could say that the entropy of the system has increased. Unfortunately, however, whenever there's an increase in the entropy of a system, there inevitably follows a decrease in the amount of energy with which we can do useful work. Extracting work from individual particles is really hard. Generally, increasing entropy is the problem with recovering wasted energy. To make matters worse, the second law of thermodynamics states that in an isolated system, entropy can only ever increase.
The second law of thermodynamics is a really interesting physical law. It has a huge range of implications, from making it impossible to create perpetual motion machines to the heat-death theory for the end of the universe. This stems from the idea of treating the universe as a closed system, whose entropy can never decrease due to the second law. So the universe will eventually reach thermodynamic equilibrium, at which point nothing can do any work.
Moving on from that slightly depressing view of the future, the second law is also the reason why time doesn't flow backwards. Because it can only ever increase, entropy allows us to distinguish the past from the future, which makes it pretty special. We could go on about the second law, but there's just one last thing relevant to using wasted energy. Heat can only spontaneously flow from hot to cold. Now, this shouldn't be too much of a surprise, because, as you know, if you put a cold object next to a hot one, it doesn't get colder. This is because of the second law.
This law has its roots in experimental observation, however it has since been proven more theoretically. Now, the reason why it's true might be surprising. Firstly, we need to distinguish between a microstate and a macrostate. A microstate is defined by the individual positions and velocities of particles within a system. A macrostate is defined by the characteristics that arise from this microstate. These are things we can easily measure, like temperature or pressure.
So you can imagine that since the microstate is so specific, it's changing all the time, way faster than we can ever hope to keep up with. But if you consider a system in equilibrium, its macrostate doesn't change anywhere near as quickly, if at all. So there are a huge number of microstates that correspond to a single macrostate. Because there are so many microstates corresponding to a particular macrostate, the change in macrostate ends up being the most likely outcome of all the possible changes in microstate. Each microstate is just as probable, so it's just a lot more likely that any change will move to a macrostate with more corresponding microstates, and therefore higher entropy.
All of this is to say that the second law is always true, on average. Statistically, it could be broken, but the chances of this happening are unbelievably small. It's worth saying that no macroscopic violation of the second law has ever been observed.
Although that hasn't stopped people from trying. There's no shortage of crazy attempts at perpetual motion, and they've been classified into categories. The first kind are machines which claim to break the law of conservation of energy. Needless to say, they don't. This second kind of machine doesn't actually violate the law of conservation of energy, because it claims to be able to convert thermal energy into mechanical energy with perfect efficiency. So there's no spontaneous energy production here, but it does violate the second law of thermodynamics, which states that whenever any real process takes place, the overall entropy must increase. And this means that the overall energy available for useful work decreases.
A good example of this is John Gamgee's zeromotor. Conceived in the 1880s, the idea here was that a ship could run on this ammonia engine without having to put in any energy. Ammonia has a boiling point of minus 33 degrees C, so at the ambient temperature it would be vaporized. This would cause it to expand and drive a piston. Sounds innocent enough so far. The problem comes from the next stage, where the idea was that the sudden expansion, along with pumping in cold air from outside, would cause the ammonia to condense, so that the cycle could restart. But the ammonia would have to be cooled below its boiling point of minus 33 degrees in order to condense. This would never happen without some external cooling. Despite the obvious silliness of his idea, he actually managed to convince a lot of people it would work, including the US President James Garfield.
But the most famous example of someone trying to get around the second law is the great James Clerk Maxwell, and his thought experiment, Maxwell's demon. In this hypothetical scenario, Maxwell imagined a demon which would control a door between two containers of gas. The demon would open the door and let the faster moving molecules move in one direction and the slower moving molecules move in the other. Since the fast moving molecules contribute more to the overall thermal energy of the gas, one container will heat up while the other cools down. This clearly violates the second law, and it sparked a lot of debate as to how to disprove it. It turns out that there's a lot more to this problem than something like a perpetual motion machine, and we can make a whole separate video about it. A simple explanation to this may be that the demon itself has some kind of entropy, and has to expend some energy in order to observe the velocities of the molecules and to see which ones to let through. This means that the entropy of the demon is increasing, and once this is taken into account, so is the overall entropy of the system.
So Maxwell's demon doesn't actually violate the second law. However, it is a very interesting experiment. In fact, Richard Feynman used something called a Brownian ratchet as an example of Maxwell's demon in order to illustrate the laws of thermodynamics. Now that we've understood the second law, let's get back to the original question. How can we convert wasted thermal energy into useful electrical energy?
This is where thermoelectric generators come in. These devices make use of a temperature difference to generate a potential difference, which, when connected across a load, can do work. This works because of the Seebeck effect, which you can observe if you heat up one end of a piece of metal while keeping the other end at room temperature. When this happens, the free electrons will develop a concentration gradient across the conductor. The concentration will be lower where the temperature is higher, just like how heating up a gas makes it less dense.
At equilibrium, this concentration gradient must be balanced out by the electric field that it generates, so there is a potential difference or voltage across the conductor. Thomas Seebeck first noticed this in the thermoelectric effect when he connected two different metals together and heated up one side. Since these are different metals, they have different Seebeck coefficients. The Seebeck coefficient basically measures the strength of the Seebeck effect for a given material. For small changes in temperature, it's given by delta V over delta T. Conventionally, the potential difference is measured from the cold side to the hot side, and the Seebeck coefficient is usually on the order of microvolts per Kelvin temperature difference.
So since the two metals have different Seebeck coefficients, the thermoelectric voltages across them will be different. This difference in voltage allows current to flow, and this is essentially how the thermoelectric generator works. Seebeck realized there was something there when it caused the needle of his compass to rotate, leading him to initially call this the thermomagnetic effect. Of course, it was later realized that the magnetic effect is due to Ampere's law, and the temperature difference was just inducing the electric field.
In practical thermoelectric generators, P and N-type semiconductors are usually used as the two different materials. With this setup, electrons and holes both diffuse towards the cold side, generating a greater potential difference than we would get if we used two different metals. So, by using P and N-type semiconductors, we allow for a larger difference in Seebeck coefficients. This is because P-type semiconductors have holes as the majority charge carriers, resulting in a negative delta V term and a positive Seebeck coefficient, whereas the N-type semiconductor will keep the negative Seebeck coefficient. The difference in Seebeck coefficients is one of the key factors in getting the most efficiency out of a thermoelectric generator, as well as high electrical conductivity of the legs to minimize resistive losses, and low thermal conductivity between the legs to maintain the temperature difference between them. And yet, even with all this taken into account, the best efficiency you'd be likely to get is around 7%, which is pretty low, but probably okay if we're using wasted heat energy anyway.
Despite their low efficiencies, there are some advantages to using thermoelectric generators. In a real thermoelectric generator module, you can see all the semiconductor couples working together to provide a more substantial current. This means that they're fairly scalable. They can produce several output power levels for different applications.
They can also be pretty compact, and since there's no dependence on gravity, they can be used in any orientation. They can work in zero-G or high-G environments, and they don't emit any greenhouse gases. Also, since there's no moving parts, they're quiet and incredibly reliable. They can also use a wide range of fuel sources. Anything that creates a temperature difference will do. This allows them to make use of wasted heat energy from things like hot water pipes, car engines, or electrical systems. In fact, we can even use body heat for certain low-power wearable tech.
Since they're so reliable and suitable for zero-G and high-G applications, one important use of thermoelectric generators is in spacecraft, like the Curiosity Mars rover or the Voyager probes. These actually use radioactive decay as their heat source, since it lasts a pretty long time, and they're actually still going over 40 years later.
It's worth mentioning that thermoelectric generators are probably different to the heat engines you may have come across in thermodynamics, since they directly turn a temperature difference into electrical energy, unlike internal combustion engines and thermal power stations.
Just like normal generators, thermoelectric ones can be operated in reverse, making use of the Peltier effect, which is basically the Seebeck effect but in reverse. So instead of using a temperature difference to generate electricity, we can use an electric current to generate a temperature difference. This has obvious uses in cooling, and Peltier elements have a bunch of industrial uses, as well as being used in some consumer devices, where the cooling is on a much smaller scale and where portability is very important, like in some electronics. However, they're also used in some advanced scientific settings like astronomical telescopes and advanced feedback circuitry.
Sadly, you won't see a Peltier-powered fridge anytime soon, since these devices are way less efficient than a normal method of refrigeration, which is based on a thermodynamic cycle of evaporation and condensation. In fact, low efficiency and high costs are the reasons why thermoelectric generators aren't being used everywhere to harvest wasted heat energy. But who knows, maybe one day we'll be able to charge our phones using energy that would otherwise have been lost to the atmosphere.